1 by V minus 1 by U, according to the mirror equation, it is 1 by F. It is an optical medium which is bounded by two surface is said to be a lens. Concave lens is a lens which diverges the beam of light which is incident on it when the concave lens is kept in the rarer medium. So this can be called as denser medium. This is called as a rarer medium. Correct from the center of this division itself, the deviation will be taking place in case of the lenses. Hello everyone, I am Vrinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 5 of chapter 9, and chapter name is Ray Optics and Optical Instruments. So in today's class, we are just dealing with something called as lens. So what is meant by a lens? You have studied about mirror, you have studied about the glass, that is a refracting surfaces and all. So lens means it is a part wherein you have two refracting surfaces. So here it is an optical medium which is bounded by two surface is said to be a lens. So it is called as a spherical lens, okay, which is of a spherical surface. So there are four types of spherical lens over here, that is two types of spherical lens, convex and concave, wherein that convex and concave can be divided into the four types, that is biconcave lens, plano-concave lens, biconvex lens and plano-convex lens. So, where and all you can find the uses of lens? It can be used in the cameras, projectors or binoculars, headlights or the side mirrors of the vehicles. All these things the lenses can be used, that is the mirrors, concave mirror, convex mirror and the lenses, okay. So these are the examples in our daily life where exactly the mirrors as well as the lens are used. So here these lenses are spherical lenses, and you have got biconcave. Bi means it is two and this is concave lens. So you know the concave lens is of this form, which is thicker at the edges than at the middle, okay. So that is known as your biconcave, or it is known as concave, and convex lens is nothing but the one which is bulged at the center. Such kind of the bulger part at the center, if the lens has got the bulge part at the center than at the edges, then it is known as convex lens. If the lens are having thinner structure in the middle and a thicker structure at the edges, then that is said to be the concave lens. Biconcave and biconvex. Bi means two sides. Two sides concave lens means the one which I have drawn over here. Two side convex lens means the one which I have drawn over here. So what is plano-concave lens and plano-convex lens? Plano-concave lens is one side it is completely plane and it is a concave lens. Plano-convex means the one side it is completely straight and you have a convex lens, the bulged part over like this. So this is all about your plano-concave lens and plano-convex lens, biconcave lens and biconvex lens. So these are the some general introduction of the lens part for us to know. Next, coming on to the concave lens, where exactly the concave lenses are used. You can see you have the following images of the concave lens as well as the concave mirrors example which is given over here. Okay, so coming to the concave lens, what exactly it does? So you have a concave lens which is drawn. So every time we consider the biconcave or biconvex lens, so if this is a principal axis which is passing through the center of the lens, you have something called as a optic center through which the principal axis has to fall. Like a pole in the mirror, you have a optic center at the center of the lens over here. So whichever parallel beam of light travels from an object towards the lens, those parallel beam appears to converge, but exactly it diverges, okay, appears to meet at a point, but it diverges. So any beam of light which is incident on the optic center, that is at the center, optic center of the lens, it appears to diverge from where exactly it meets. That is, from the optic center, it starts diverging. This is how you give the concave lens introduction. That is, concave lens is a lens which diverges the beam of light which is incident on it when the concave lens is kept in the rarer medium. So this can be called as denser medium. This is called as a rarer medium. Now coming on to the convex lens, you have got the convex lens given as the biconvex lens, whatever you consider. So here you have a principal axis which passes through the optic center, and finally whichever light passes through the optic center, it converges at a focal point. So the parallel beam of light from the optic center, it starts bending. So it bends towards the principal focus. So that is why this convex lens, when placed in the rarer medium, it is called as a converging lens. Okay. So I hope you are clear with the converging lens as well as diverging lens. Having these concepts, let us go something deep into the lens thing, that is the components of the lens. Let us know some basic components of the lens. So you have got a lens where I consider a convex lens for now. So a convex lens, it has got a principal axis. So the axis which passes through the center is known as a principal axis. And at the center of the lens, when we bisect it, this part is said to be optic center, which is called as O. So you're done with principal axis and optic center. Each one of the sides, that is each one of the lens, this is a thin lens, okay? So two thin lenses are combined together. So each side of the lens, this curved part, if suppose if there is a circle over here, this is a spherical. So from the spherical, we are just taking a part of spherical surface, then its radius of curvature, that is center of curvature is this, radius of curvature will be this part. So similarly, if you're considering the other side of portion of the lens, if suppose that has got the circle in this manner, even that will also have center of curvature, call this as C1, call this as C2, and this also will be the radius of curvature. That starts from the optic center. Everywhere we take the optic center as a reference point or the referral point. Clear? So now we are done with your principal axis, optic center, center of curvature, radius of curvature. Same thing goes with the principal focus. So here it will be F1, here it will be F2. That will be the principal focus with the focal length of small letter F1 and small letter F2. So suppose if this is F1, this is F2, the distance between these two will be F, and this also will be F. So that is all about the components of the lens. Next we are skipping on to the lens maker's formula, which is very important for 5 marks, and it is a sure question, 100% sure question is your lens maker's formula from this chapter, which carries 5 marks. When that is the case, you will have to have a hawk eye on this derivation, that is lens maker's formula. For this lens maker's formula, we are supposed to consider a convex lens, okay? So it's a thin lens which is completely fixed together. It is like two planar convex lenses fixed together. So I'll just draw the convex lens which is present over here. So this can be the convex lens. And now draw a principal axis which passes through the center. Okay, so now suppose if there is a object, call it as O, and let this be the optic center, and the imaginary line, just imagine there is a line which passes through it, from where exactly the deviation has to take place. Correct from the center of this division itself, the deviation will be taking place in case of the lenses. But in the refracting material, when the light ray passes from rarer to denser, there is a bending of light, correct? So let us go through that refracting surface techniques. Okay, so now there is a object, call it as O, which is placed at certain distance. We don't know which distance exactly it is, but it is at a certain distance from the optic center. Clear? Now there is a incident beam which falls onto the lens. So suppose you consider a incident beam which is falling on the lens. Okay, this is the incident beam, and you just draw a normal to the incident ray as per the rules, that is as per the laws of refraction. Clear? And now when there is a normal from the rarer to denser medium, and when a beam of light passes from rarer to denser medium, what happens to the refracted ray? It bends towards the normal. So let me draw just the bending up towards the normal, and we have got our bending over there. Okay, again you will have to draw, if now this is the incident ray which goes out of the lens towards the rarer medium. When that is the case, you will have to draw a normal once again, which makes an angle of incidence over here. So now when it travels from denser to rarer medium, the ray should move away from the normal. So it bends completely in this manner. Okay, so you have your object over here. So from here to here, the distance is called as object, and from here to here, the distance is called as image distance, call this as I. So you have object over here, image over there. So the lens is of A, B, C and D, and the point of intersection, this is P and this is Q. So now let us give a description to this. First of all, you will have to draw a diagram, then give the description. Like, consider a lens, that is a convex lens, of sides A, B, C and D. Lens is over. Now, consider an object, that is a point object, which is placed at a certain distance from the optic center. Okay, after which it will be like the incident beam from that point object is incident on the refracting surface, not reflecting, it is refracting surface. Clear? So when it is incident, it gets refracted at the point P and Q, and finally we obtain the image at I at a distance V from the optic center. So I hope you're clear with the description now. You got your diagram, you got your description. After which you will have to start up with the exact derivation of it. So now, in order to start up, we have to divide into components. Suppose if I give you hundreds of chocolates and ask you to count just in 5 to 10 minutes like that. So you need some help, correct? So in order to take a help, what do? You just call your friend and you share 50 and 50, or you call extra 2 of the friends, that is total of 4 members, sit and count 25. In short, you will get to know what is the exact count in that chocolate box, correct? Similar way, our duty is to divide the mirror now. Okay, so that is, let us divide this mirror, that is likewise, it's our duty to divide the lens. So let us divide the lens which is there here right now. So now, considering the lens, that is half of the lens A, B, C, and next it will be consider A, D, C. The 2 of the sides we are supposed to consider. So now I'll consider only A, B, C portion now. Okay, so this is a principal axis which is passing through it. So this point is called as A, this is B and this is C. Let me extend my principal axis a little more. Okay, so suppose if there is an object which is placed over here O, and the incident beam is incident on it, there is a normal which is drawn, and you have a refracted ray towards the normal. So you just extend this normal, you will have C1 over here, and the image, virtual image what is formed will be I1 over here. I hope you're clear with these things. So you have a point that is called as P, which is intersecting over here. Okay, the same thing goes up with the ADC part. So if suppose you consider part ADC and there is a principal axis which is passing through, this is called as A, this is called as D, and this part is called as C. Now the virtual image what is formed over here, that is I1, is nothing but, for the second mirror, it is considered as an object. So the object is placed over here, again the light falls. It's like that. So I1 will be the object, that is the I1. The ray I1 is there, no? This ray is called as the ray of the object. So you'll have to continue with the same ray of object and carry on with this. You have a refracted ray in this way and the normal which is drawn such that it makes certain angle with this line, and then it moves away from the normal. So now the extension of this line will give you I dash, that is an imaginary image, and here you have I, the actual image. Okay, so this is how exactly it has to take place, and this part is called as Q. So this is how the total refraction takes place in the biconvex lens, which is divided into two halves. In case of ABC and ADC lens part, how exactly the refraction takes place. So at this part the normal just extended, so this part will be C2. So I hope you are clear with the diagrams how exactly it has to be given. So now from the first part of the lens we have to calculate for the refraction at spherical surface. First spherical surface what we consider will be ABC. So now for the spherical surface ABC, the refraction at spherical surface is given as N2, that is refractive index of the denser medium. So this is the refractive index of the denser medium. This is the refractive index of the rarer medium, and where exactly the object is placed, that is this part. We are considering the first spherical mirror. So first spherical lens will be having the radius of curvature R1 and the second spherical lens will be having the radius of curvature R2. So here we are supposed to consider R2 for the refraction at the spherical surface, which we had already derived, and we have a formula for it. And the general formula which is given as N2 by V minus N1 by U is equal to N2 minus N1 divided by R1. This is the general formula what we have. We will have to substitute for this, and now we have the object which is placed at U. The object, in this case, the object is at U distance and the virtual image is at I1. That means the virtual image the distance of the virtual image can be known as V1. So here we have N2 divided by that. In case of denser medium, there is a virtual image which is created. So I'll just give V1 minus N1 divided by U is equal to, because N1 is a rarer medium in which the object is placed and object distance is U, and now N2 minus N1 divided by R1. This is just R, so here we have R1. Okay, so next coming on to the, this will be the refraction at the ABC spherical surface. This is the first part of the set. Okay, so now we have the second part of the set. Call it as for the spherical surface. For the spherical surface ADC. So now we have, this is the image part. So now at the second place, the image is formed in the rarer medium, and the object, that is the virtual object what we consider, will be in the denser medium. So now we have the image part as N1 because it's formed in the rarer medium, divided by V is the actual distance from the optic center to the actual image formed. So it is written as V. And the object what is considered will be at the distance v1 because the image, that is a virtual image, what was formed in case of the first refracting surface is now considered as the object. That is why you are considering the place of object place distance v1. Okay, next it is n1. So object is considered in the refractive index n2, that is why it is given as n2, which is equal to n1 minus n2 divided by r2. So I have to get this form, that is our right hand side, to the same form. So I'll just cross it over. So I'll get minus r2 v minus n2 by v1 is equal to n2 minus n1 divided by minus r2. So call this set of equation as equation, this is 1 and this equation is equation 2. Now on having two set of equation, we will have to add up one equation and the second equation. So on adding, what do you get? n2 by v1 minus n1 by u, add all LHS part, plus n1 by v minus n2 by v1, which is equal to n2 minus n1 divided by r1, and I'll just continue over here. It is plus n2 minus n1 divided by minus of r2. This is the set of equation. First equation, second equation, both left hand sides. First equation and second equations, both right hand side, together you are equating. Now you will have to cancel the common terms. How is that? n2 by v1 is positive. It cancels with negative of n2 by v1. Both are one and the same. Just that what changes is the sign. So next we have minus n1 by u plus n1 by v is equal to, take the common out, n2 minus n1 both are common. So what remains is 1 divided by r1 plus into minus, it is minus 1 by r2. This is the other set of equation. Next we are going on with n1 is common, which is taken out. So it is like 1 by v minus 1 by u, because positive sign I'll just consider first and the negative sign next. But the common term out of these two is said to be n1, which is equal to n2 minus n1 into 1 by r1 minus 1 by r2. So this is the equation what we have. And now n1 is taken to the denominator. So 1 by v minus 1 by u is equal to n2 divided by n1 minus n1 by n1, and you have 1 by r1 minus 1 by r2. n1 cancels and we get 1 by v minus 1 by u is equal to n2 by n1 minus 1 into 1 by r1 minus 1 by r2. According to the Snell's law, this can be written in terms of the refractive index. Okay, refractive index of the first medium with respect to the second medium can be written over here. So 1 by v minus 1 by u, according to the mirror equation, it is 1 by f. So 1 by f is equal to n2 to 1 minus 1 into 1 by r1 minus 1 by r2. So this is the final set of equation which is known as the lens maker's formula. Very important, and for 5 marks it comes, and it is a sure question which comes in the part D section of the question paper in the 5th Roman number. Okay, so that is all about your lens maker's formula, and this lens maker's formula is used in order to design a desired lens of certain focal length. Okay, so now this is applicable for convex as well as concave mirror, both also. So in today's class we have dealt with the lens, spherical lens, types of lens, and the components of the lens as well as lens maker's formula, which is very, very, very important for the exam. Okay, so let us all meet in the next upcoming session with the same chapter. Until then, have a good day. Thank you.